right, today we're going to talk about sections 9.4 and 9.5. So 9.4, we're going into thermodynamic and kinetic control. So kinetic control basically just means that you have a reaction that's happening very slowly, maybe so slowly that you can't even measure its rate. It's still spontaneous though, so it has a negative delta G. So the reason that it's happening slowly is simply that it has a really high activation energy. So if you look at this decomposition of peroxide, hydrogen peroxide, you can see here it's turning into water and oxygen, and there's a big activation energy. We do have an overall drop in free energy here. We're going down in free energy. But it's going to happen very slowly. You leave a bottle of hydrogen peroxide open, this reaction will happen naturally, but it'll take uh, you know days, perhaps even weeks before you're going to end up with just a bottle of liquid water. It is important to note that this does not mean the reaction is at equilibrium. This is a one-way reaction in this case. Equilibrium cases we'll talk about here in just a bit. This is a reaction that goes to completion. So if we wanted to speed this thing up, we could do that by adding a catalyst. So if we add some like manganese or manganese dioxide catalyst to this, going to give it a different pathway to take with a lower activation energy. And so this is going to result in the reaction speeding up. So, but it's still going to have the same delta G, because that delta G, remember, is just looking at the difference between the reactants and the products, and that part hasn't changed. We're just making the reaction happen faster. Okay, so here is an example for your response. Answer the following questions in terms of thermodynamic principles and concepts of kinetic molecular theory. So consider the reaction represented below, which is thermodynamically favorable at 298 kelvins. So it's spontaneous. They give you the reaction, and it says for the reaction, indicate whether the standard entropy change, delta S, is positive, negative, or zero, and justify your answer. So give that a couple seconds and think about that. All right, and so hopefully you answered negative, and you would say that because we have 3 moles of gas going to 0 moles of gas, right? 3 moles of gas on the left, 0 on the right. All right, so which factor, the change in enthalpy or the change in entropy, provides the principal driving force for the reaction? All right, so think about that. We just said that we had a negative delta S probably, and the problem says we have a negative delta H. So which one is the driving force? Okay, so hopefully you said the negative delta H, the exothermic nature of the reaction, and that is because negative delta S, decreasing randomness, is not favorable. All right, and then how is the standard free energy change affected by an increase in temperature? And then explain. All right, so since this is an exothermic reaction, if we increase the temperature and we have that negative delta S, we should see our delta G increase. In other words, become less likely to be spontaneous. So at higher temperatures, the product of T times delta S is going to be a larger negative value. So subtracting that is going to give our delta G a bigger chance to be positive. All right, and then some reactions that are predicted based on the sign of their delta G to be thermodynamically favorable at room temperature do not go very fast. What is the reason for this? And this is what we just talked about. So spontaneous reaction doesn't have to happen at a high rate. If it's under kinetic control, it just means it has a high activation energy, but that still can have a negative delta G. All right, and then a suitable catalyst increases the rate of such a reaction. What effect does the catalyst have on delta G of the reaction. What do we think about that one? So hopefully you said none. It will have no effect on delta G, right? It's just giving it a different pathway to take with a lower activation energy. Okay, so let's go ahead and talk about section 9.5, equilibrium and free energies. And now we're going to talk about reversible reactions. When we have a reversible reaction, we can tell if the forward reaction is spontaneous at a given temperature using the K. And we can do that using this equation. So we have yet another delta G equation here. Delta G equals negative R, that's a constant, and that is 8.314, so it's the same as our gas constant for kPa, times temperature, of course in kelvins, times the natural log of K, or Kp, or Kc, or whatever we want to call it for our reversible reaction. All right, so problem says determine the delta G in kilojoules per mole of N2 for the following reaction at 298 K. And it gives you the value for K, 1.6 times 10 to the minus 3 for this reaction at that temperature. So it's pretty much just a matter of plug and chug into our calculator. We're going to put in the negative, don't forget that negative sign, of our R value times the temperature times the natural log of our K value, which was given to us as 1.6 times 10 to the minus 3. Again, this is temperature dependent. Now, do note here, this is going to give us our answer in joules. We're used to seeing it in kilojoules, and in fact, that's what this question asks for. So when you get 15,900, recognize that that is in joules because our R value has joules in the numerator there. So we are going to have to divide by 1,000 to get that to 15.9 kilojoules. Now, what does this mean in terms of like qualitatively looking at the problem? What does it mean about that forward reaction that we have this positive value for delta G? Well, we know it means it's non-spontaneous, right? And that hopefully should make sense. If we have a positive value for delta G and it's non-spontaneous, that means that this forward reaction is not thermodynamically favored, and it should make sense that our K value would be less than 1. And in fact, in this case, pretty much less than 1, 0.0016. And so we can say that a small K value is going to lead to a large, or in other words, positive delta G. And of course, then hopefully it makes sense that the opposite would be true as well. A large K value means a small or negative, and therefore spontaneous delta G. All right, let's try one more type of problem. So this time we're just using the same equation, but we're going to use it to find Kc. K, Kc, Kp, it's all the same. We're just trying to find that K value. So here we have the synthesis of ammonia. It's at a very high temperature, 773 kelvins. So let's see if we can figure out the delta G for this reaction. Figure out the Kc for this reaction if the delta G is positive 11 kilojoules per mole at that temperature. All right, so we have our equation that we just learned, right? This time, though, we know the delta G. We don't know the value for K, but we do, of course, know R, and we know temperature. So it should just be a matter of rearranging the equation. All right. So rearranging it's a little bit tricky because we've got that natural log in there, but essentially it's just going to become K equals e to the negative delta G over R times T. And so once we get to that point, it's just a matter of, again, just kind of plug and chug. And so we get K equals e to the negative 11,000. Make sure you're careful about changing those kilojoules to joules, because our R value is going to be based in joules. I didn't bother, though, with labeling units here because K is not going to have a unit. And then once we do all the math there, we get about 0.18. So that should make sense, I think, because we have a positive delta G once again. It's not thermodynamically favored in the forward direction. And so we did end up getting a K value that was less than 1.